Okay, so welcome back again, another video. So in this video, we are going to talk about the acidity. So here you have the phenol, and here you have the phenol with the nitro group attached to it. So we are going to talk about like how these attached groups affects this phenol's acidity. First of all, let me introduce to you this acidity. Okay, this is very important. Like you need to understand this concept in very clearly. So here you have the phenol, okay, and what is mean by acidity? Acidity means like the ability to remove your positive, like proton, right? Ability to remove your proton. So when you remove this phenol's acidity, proton, you have a structure like this. Okay, now here we have the phenate anion. Okay, so this is phenol, this is phenate. So now like I can say a thing like this: if this reaction is much more feasible, like this reaction rate is higher, this reaction is much more efficient, then this particular compound's acidity is higher. You can agree with me, right? So when the reaction rate is higher, when the reaction is happening rapidly, the more H plus ions will be removed, which means the removal of H plus ions are very feasible. So acidity is higher. So now in order to be feasible, like in order to this reaction to be happen faster, this final product has to be stabilized. If this final product here is not stabilized, if this is destabilized, this reaction won't occur, right? This reaction won't try to go into this state because this is destabilized. Every compound in our nature tries to be stabilized. If this is much relatively destabilized, if this is not stable enough, then this reaction rate won't be that much efficient, like it won't be that much rapid. So what we have to think about is, more stable this final product gets, higher the acidity, because more stable this product is, higher the reaction rate. Higher the reaction rate means more rapidly these protons are leaving. So how can we stabilize this compound? How can we stabilize this compound? Basically by delocalizing this negative charge or neutralizing this negative charge. So you need to see whether the effects on this particular final product is neutralizing this particular charge, then it has more tendency to neutralize it, or it has more tendency to delocalize it, which means we can make this final product, this phenate ion, more stable. Okay, so in these phenols we can draw resonance structures. Okay, so we can draw resonance structures like this. So let me draw the resonance structures for you. You can draw resonance structures for this anion. So you can move this here and move it here. Now you have a molecule like this. You have a positive charge and you have a negative charge here. And now you can move it into this. Because of that, this will move here. So you will have the product like this. And then likewise, we can have product like. So you can see that this final product is delocalized, right? This anion is delocalized, which means this is particularly stable because of the delocalization. So that's why we are saying phenol has relatively high acidity, because its final product is stable. So this reaction is much more feasible. So this removal of proton is much more efficient. So we can say phenol is much more acidic. Now let's see how this like NO2 group or any other group affects this acidity. Okay, now here we have the phenate ion. Okay, here we have the phenate ion. Now you can see if we can like withdraw this electron density away from this oxygen atom, and you know this oxygen atom is negatively charged, which means it has a high electron density. So if we can withdraw electron from it, this becomes neutralized, right? Because we are pulling away this negative charge, which means we are neutralizing this negative charge. So by introducing a electron withdrawing group, NO2 is an electron withdrawing group. If you remember these things, like we have talked about these substitution reactions, how this meta orthopara, likewise this how this directing happen, how to activating, how this activation of benzene ring, deactivation of benzene ring, we have talked about it. So like if you don't remember about it, so I highly recommend you to go back to that video. I will put the link here so you can watch it. Like that knowledge is essential for this particular theory part. Okay, now you have to know that NO2 is a electron withdrawing group, so it can pull away electrons. So it can pull away electrons from the benzene ring, which means this electron density is pulling away. So with an introducing of this electron withdrawing group, we can increase the stability, right? We can increase the stability. So in any case, so here you have the phenol, here you have the phenol. If you add the electron withdrawing group to any place, right, here you have the phenol. So if you add the electron withdrawing group to any place, so here this is E, this is an electron withdrawing group. Okay, this is an electron withdrawing group. So if you add the electron withdrawing group either here, 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 or here, you can achieve more acidity than the phenol, because like rather than the phenol, you are pulling away the electron density, which means you are relatively make it stabilized rather than the phenetide. So it doesn't matter for now the position, right? It doesn't matter the position for now. Like at least you are attaching an electron withdrawing group, you can pull away the electron density, you can stabilize the final this anion. Now what will happen if you introduce a electron donating group like NH2 group? Let's say NH2 group is here. Now here you have the phenol. Now what happens? These are electron donating groups, right? So what happens is it's donating electron density. It's donating electron density towards the benzene. So this particular oxygen's electron density cannot move into the benzene ring, because like benzene ring already gets electron density from here. So it's stuck on this place. So this negative charge, it not getting reduced, it getting increased due to this electron pushing effect, this electron donating effect. So you know, like higher the charge it becomes, it getting destabilized. Because like in order to stabilize, we need to make it neutral, right? We need to reduce this negative charge. But in this case, what happens when NH2 groups or electron donating groups pushing electron density towards your benzene ring, this oxygen cannot push away its electron density away, it has to take it for itself. So now this is getting destabilized. So anyway, if you have an electron donating group in your benzene ring with your phenol, okay, here electron donating group, I will put it like D. So this is electron donating group. Okay, it is destabilizing your final product, which means the reaction here, the reaction is not likely to be feasible. Like it doesn't like to go into this particular final state, so it lacks the efficiency. So this removal of proton is not that much efficient, so acidity is getting lower. So here you have the lower acidity. Now let's look at the position. So let me take this particular molecule to explain what happens. Okay, if you remember our final video about the orthopara directing and meta directing compounds, okay, here I have drawn the nitrobenzene to explain the electron withdrawing group effect. If I ask you due to this NO2 groups, like what effect would be happen to this particular position. If you remember closely, this place getting relatively positive, this place getting relatively positive, this place getting relatively positive. So like basically both meta positions are relatively higher in charge, it not getting any affected by NO2 groups. Okay, so like it getting less effective, but these places are becoming more electropositive. Now if you remember our product, we have the product with here, we have phenol OH group here. Now you can see when you add your NO2 group or your electron withdrawing group into a para position, this particular electron withdrawing group can make this position electropositive, right? This position electropositive. So when you make the anion here, you can see if you make this particular position positive, which means this particular electron density is much more efficiently flow through into the benzene ring, because this is positive, right? This is negative, this is positive, so this electron density is going through easily, right? But what if you have your electron withdrawing group? Okay, what if you have electron withdrawing group into place like this? So you have it like into this place. Now respect to NO2 group, your this OH group is on the meta position, right? So if I ask you what are the positive positions, this is positive, this is positive, and this is positive. This is ortho and this is para. These are meta positions. Right? So now you can see this particular position has not gained any positively charge. So like here, unlike here, this doesn't have that extra ability to withdraw electrons. So if you compare these two guys, you can see more electron flow away from this oxygen is happening in this particular compound. So I can put this particular compound as higher acidity because it's withdrawing away this negatively charged much efficiently. Okay, so here we have the OH in para position. We have the acidity, and here in this case you can see it's relatively a little bit low. Okay, it's relatively a little bit low. So let me draw it like this. Okay, here you have the NO2 and OH. Okay, now what about this place? If you attach your NO2 group into this place, now your group is here. Now you can see that the positive charge is there, right? Positive charge is there. Now that the electron flow is efficient, so this has relatively good stability rather than this. But compared to this has lower stability. Like this has lower acidity. So if I draw the structures like the order, let me erase this guy. So when you are in this guy happens, now you have the NO2 here and OH here. Now this is in the place like this, right, in the middle of these two. Why is that? Why cannot this guy like overtake this one? Because of the sterical hindrance, right? You can see this is a little bit steric hindrance. There are steric hindrance occurring. So like when you talk about the anionic form, due to the steric hindrance, this getting more energy, this getting more potential energy, so it getting destabilized due to this. But it has higher stability, like it has higher acidity than this meta position. Okay, because like in this case you have positive charges on this particular position, but you can hear positive charge on this particular position. I hope you get the idea about the electron withdrawing. The same thing happened with the electron donating groups. If you look at the electron donating groups, here you have the OH, here you have the electron donating like NH2, let's say. You can see like these positions are getting negative. So like if you have a negative charge in this position, this is very bad, right? So like you have this oxygen is negatively charged, you need to take it away, right? But you cannot do it because there's a negative charge in this place also. So this is like really unstable. This is really unstable. So in this case, you have this guy which is much more unstable, so has lower acidity compared to meta position. So you can see like in this position, relatively this positions lacks the electron density. Relatively this is neutral, yes, this is not positive, but it doesn't contain any negative charge, right? So relatively this position, this is very good at least for these molecules. So in this case, you have the order like this. This has high electron density. Sorry, this has higher acidity than this. Okay, so I hope you get the idea about this acidity part. Like if you had like 2-3 NO2 groups, then like the acidity increases drastically, right? You can get the idea about, right? If you add another NO2 group here, then this is the highest acidity because there's 2 NO2 groups withdrawing electrons. Okay, so it doesn't matter even the second NO2 group is at the meta position because like both is affecting the phenetime, so the final anion. So I hope you get the idea. Like what you need to know about is the stability of this anion. If you can make this anion much more stable, which means you can efficiently remove this proton, so you can higher the acidity. You can say it's high in acidity. I hope you get the idea about it. So like let's do some questions in our next video so you can get the theory well aware.